In 2025, quantum computing reached a point where breakthroughs were happening almost monthly. These weren't just small lab experiments. They were milestones that could change everything, from the way we power our cities to how fast we develop life-saving medicines, and even how we understand the universe itself. And the most shocking discovery of all? A machine so advanced. Some experts say it could rewrite the entire future of technology. Stay until the end, because what Microsoft revealed this year may be the single biggest leap in computing history. But before we get there, let's start with how quantum computing is already changing the world in ways you'd never expect. Running a modern power grid is like juggling thousands of airplanes, all taking off and landing at the same time, without a single delay. Every gust of wind, every spike in demand, every sudden dip in solar power adds another layer of chaos. The possibilities balloon so quickly that even the world's fastest supercomputers buckle under the strain. For decades, this has been one of the holy grails of computing. How do you keep the lights on when everything is unpredictable? In 2025, that wall finally cracked. A collaboration between IonQ and Oak Ridge National Laboratory unveiled a hybrid quantum classical solver that attacked one of the hardest problems in energy management: scheduling generators across a 24-hour cycle while accounting for fluctuating renewables. Their 36-qubit system wasn't just a proof of concept. It showed that quantum processors could actually optimize renewable heavy grids in real time. Imagine a control center that can predict a wind drop 15 minutes ahead, reshuffle the power mix instantly, and prevent a blackout before it even begins. That's what we're talking about. And it doesn't stop at electricity. The same quantum techniques were deployed to model tsunamis, fluid flows, and atmospheric shifts at scales and speeds traditional HPC systems simply couldn't match. Think of it this way. If classical computers are sketching weather patterns with a wide brush, quantum systems are adding in the fine details, the ripples, eddies, and fault line shifts that could mean the difference between a warning and a catastrophe. A tsunami predicted 3 hours earlier isn't just an improvement, it's thousands of lives saved. Why does this matter so much? Because the global energy transition is already underway, and it's fragile. Renewables are clean but volatile. Grids need millisecond-level coordination to balance them. With quantum, planners can cut costs, smooth out the peaks and valleys, and accelerate the shift away from fossil fuels without sacrificing reliability. And here's the twist. This isn't just about grids or climate. The very same breakthroughs in quantum optimization are being adapted to something far more personal: human health. Designing a new drug is like trying to solve a puzzle where the pieces are constantly shifting shape. Proteins fold in mind-bendingly complex ways. RNA spirals into tangled knots, and the number of possible configurations explodes faster than any classical computer can track. For decades, pharmaceutical labs have relied on trial, error, and brute force simulations. Processes so slow that a single drug can take over a decade to reach the market. Enter quantum. In 2025, we saw the first real cracks in that bottleneck. IBM's Heron chip successfully modeled RNA structures up to 60 nucleotides long. The kind of calculation that would bog down classical supercomputers for months. At the same time, IonQ and Capua Quantum achieved something that biologists had been chasing for years: simulating protein folding for sequences of up to 12 amino acids. These may sound like toy problems compared to the vast machinery of life, but in drug discovery, even a modest leap in accuracy can shave years off the development cycle. Here's what that means in practice. Vaccines designed not in 18 months, but in 6 weeks. Cancer therapies tailored not to patients like you, but to your exact genome. Antiviral drugs tested against millions of potential mutations before the virus even has a chance to spread. Quantum isn't just accelerating science. It's collapsing the distance between a medical idea and a working treatment. Think back to the early pandemic. Researchers scrambled to model spike proteins, test vaccine candidates, and optimize doses. With quantum-level simulations, that frantic 18-month timeline could shrink to weeks. In a world where speed equals survival, this isn't just a scientific breakthrough, it's a lifeline. But here's the catch. As revolutionary as these quantum-driven discoveries are, they come with one massive problem. Quantum computers are still notoriously unreliable. Here's the brutal truth. Quantum computers are powerful, but they're also fragile. Every qubit is like a violin string balanced on a razor's edge. The slightest vibration, a whisper of heat, or even background radiation can send it out of tune. And unlike classical bits, which are either 0 or 1, qubits exist in delicate superpositions. Once errors creep in, they multiply fast. The more qubits you add, the noisier the system becomes. It's like trying to build a skyscraper on shifting sand. That's why scientists call fault tolerance the holy grail of quantum computing. Machines that can not only perform calculations, but also detect and repair their own mistakes as they go. Without it, quantum computers will always be stuck in the realm of flashy demos and toy problems. With it, they become engines of discovery. In 2025, the race for error correction exploded into a full-blown sprint. DARPA's US-2QC program, run by the same agency that helped birth the Internet, GPS, and stealth technology, pushed Microsoft and PsiQuantum into the final phase of building a fault-tolerant quantum machine. This wasn't just a research project anymore. It was a declaration. Error-corrected quantum computers are now a matter of national strategy. Meanwhile, something even more astonishing happened. A team at Chuera pulled off a feat that scientists had been chasing for over 2 decades. Large-scale magic state distillation. Think of it like a water filter, but for quantum states. You feed in messy, error-prone qubits, and out comes a clean, reliable magic state that can be used for long, complex calculations. For years, this was only a theory, a what-if scribbled on whiteboards. In 2025, it became real. Why does this matter? Because the moment you crack error correction, the rules of the game change. Suddenly, quantum computers aren't limited to shallow, short-lived algorithms. They can run marathon-length computations without collapsing under noise. That's when the real revolution begins. When quantum goes from experimental to industrial. And here's the kicker. Once you tame errors, you unlock the ability to tackle problems so vast, so fundamental, that they brush against the very laws of the universe itself. Quantum computing isn't just about solving business problems, curing diseases, or keeping the lights on. Sometimes, it points its spotlight at the biggest question of all. What is the universe really made of? In 2025, D-Wave's annealers crossed a threshold no classical supercomputer could approach. They simulated the behavior of exotic magnetic materials at a scale so vast, the equations would have taken years to crunch on even the fastest high-performance machines. This wasn't a toy calculation. It was real physics that could guide the design of next-generation superconductors and quantum materials. But then things took an even wilder turn. Researchers used those same systems to probe a phenomenon out of quantum field theory called false vacuum decay. Imagine the fabric of the universe sitting in a resting state, like a ball perched in a shallow valley. But hidden somewhere nearby is a deeper valley, a lower energy state. If the ball ever tunnels through the hill and falls into that valley, the entire universe could undergo a catastrophic shift in its fundamental laws of physics. It sounds like science fiction, but it's a real theoretical possibility. Classical supercomputers choke on equations like this. The math grows too wild, too fast. But on D-Wave's quantum annealers, for the first time, scientists could simulate these transitions and actually map out scenarios for how such a decay might occur. In other words, We're beginning to use quantum machines to explore the quantum universe itself. Why does this matter? Because for decades, questions about dark energy, exotic particles, and the ultimate fate of the cosmos have been trapped in the realm of pure theory. Now, with quantum computers, we have a tool that can finally begin to test those theories in silico. It's not just engineering anymore. It's a new lens into reality. And yet, for all the wonder these experiments inspire, they don't answer the question keeping CEOs, governments, and engineers up at night. The race doesn't come down to who can simulate false vacuums or model exotic physics. It comes down to something much more practical, much more brutal. Who can build the most powerful, reliable hardware first? For years, quantum computing felt like running in quicksand. Every time researchers tried to scale up, the ground gave way beneath them. Add more qubits, and instead of gaining power, you invited chaos, noise, decoherence, and error rates that ballooned until the system was practically useless. Progress slowed to a crawl. The field needed a breakthrough, not in theory, but in practice. In 2025, Google delivered it. Their new Willow processor, a 105-qubit superconducting chip, flipped the script on everything we thought we knew about scaling quantum hardware. Instead of collapsing under pressure, Willow did the unthinkable. It achieved below-threshold error correction. In plain terms, this meant something almost magical. For the first time in history, adding more qubits didn't make the machine less stable. It made it more reliable. This is a watershed moment. Imagine building a bridge where every extra beam doesn't add weight, but instead makes the whole structure sturdier. That's what Willow represents. Until now, error correction felt like patching holes in a sinking ship. With Willow, quantum computing finally has a path where scaling up doesn't just mean bigger, it means better. If this result can be sustained, and that's the big if hanging over the field, it marks the end of the toy era. No longer are these machines just playgrounds for physicists chasing elegant demos. We're now looking at devices that could run complex, real-world algorithms for hours or even days at a time without collapsing into noise. Optimization, chemistry, machine learning. All the big promises of quantum suddenly feel one step closer. And here's the twist. While Google was making this leap in the West, Asia wasn't watching from the sidelines. They were quietly preparing their own power move. In April 2025, Japan shocked the quantum world. Fujitsu, in partnership with Riken, unveiled a 256-qubit superconducting quantum computer, a massive leap forward that quadrupled their earlier 64-qubit system. Overnight, Japan went from being a quiet observer to owning one of the most powerful quantum machines on the planet. For decades, the global quantum race was largely a two-contender story. The United States, with giants like Google, IBM, and Microsoft, and Europe, with its ecosystem of startups and government-backed programs, dominated headlines. Asia, while active, was often seen as trailing behind. But this unveiling changed the narrative. Japan's move wasn't just about numbers on a spec sheet. It was a declaration. Asia is here, and it's ready to compete. With countries like China pouring billions into photonic and superconducting systems, and South Korea investing heavily in national quantum programs, the competition is no longer regional. It's global, fast, and more intense than ever. And there's a deeper significance here. Scaling qubits is one part of the challenge, but it isn't everything. Anyone can build a bigger system on paper. What matters is precision and fidelity, how accurately those qubits perform, and whether they can be trusted to run algorithms at scale. Japan's new machine, backed by its reputation for engineering excellence, wasn't just a size upgrade. It was designed to hit the kind of reliability metrics needed to push the field forward in a meaningful way. The result? A world where breakthroughs no longer trickle out of just one or two labs in Silicon Valley or Europe, but where discoveries spark across multiple continents, creating a kind of global arms race for innovation. Each new leap raises the bar for everyone else, accelerating progress at a pace we've never seen before. But here's the thing. While size and scale make headlines, accuracy is the real battleground. And that's exactly where the next breakthrough came in. At its core, quantum computing is about trust. You can have the biggest machine in the world, but if its operations fail too often, the whole system collapses like a house of cards. That's why fidelity, the measure of how often a quantum operation works exactly as intended, is one of the most critical benchmarks in the field. The closer you get to 100%, the closer you are to a machine that doesn't just show off in the lab, but actually solves problems reliably in the real world. In 2025, Rigetti's Anka 3 superconducting processor delivered a shock to the industry. It achieved 99.5% fidelity on 2-qubit operations, the highest ever on its platform, and a milestone that many thought would take years longer to reach. This wasn't just a vanity number. Hitting that level of accuracy meant Rigetti crossed into a territory where you can begin to chain together long computations without watching error rates spiral out of control. For context, 2-qubit operations are the heart of quantum algorithms. They're like the glue that lets qubits talk to each other and work as a team. If that glue is weak, your entire system falls apart. At 99.5% fidelity, Rigetti proved that superconducting systems, once criticized as too noisy, too unstable, and inferior to rivals like trapped ions or neutral atoms, are not only surviving but thriving. And the symbolism here matters. Rigetti isn't Google or IBM with billion-dollar research budgets. It's a smaller player that has fought for relevance in a crowded field. By hitting this milestone, they showed that innovation doesn't just belong to the giants. Startups, with the right breakthroughs, can push the entire industry forward. Skeptics who dismissed superconducting qubits as a dead end now have to take a second look. Because if fidelity keeps climbing at this pace, superconductors could remain a dominant architecture in the race to fault tolerance. Not a relic. But fidelity is only half the story. Precision gives you reliability, yes, but scale is what turns a lab experiment into a world-changing machine. And while Rigetti was pushing fidelity to new heights, another group was working on scaling qubits by the thousands. Not with superconductors, but with neutral atom machines. If superconducting qubits are the heavy machinery of quantum computing, neutral atom systems are the elegant alternative, vast, precise, and almost otherworldly. Picture this. Thousands of atoms, each one smaller than a grain of dust, held perfectly still by beams of laser light. They don't drift, they don't wobble. They just hover, like marbles suspended in an invisible grid. It sounds like science fiction, but in 2025, Caltech researchers made it real. They scaled their optical tweezer arrays to hold over 6,000 atoms at once. To put that in perspective, most quantum computers today brag about reaching a few hundred qubits. 6,000 isn't just a leap. It's a whole new scale of ambition. And the kicker? Those atoms maintained coherence times of 12 seconds. In quantum terms, 12 seconds is practically an eternity. That's like giving a sprinter hours to finish a race without losing speed. But scale without accuracy is just chaos. What made this achievement even more jaw-dropping was the precision. The team demonstrated 2-qubit gate fidelities above 99.5% across dozens of atoms. In other words, not only could they wrangle thousands of qubits into place, but those qubits actually performed their operations with a reliability that rivals the very best superconducting or trapped ion systems. This combination, massive scale and near-perfect precision, is what has many scientists convinced that neutral atoms might be the dark horse of the entire quantum race. Unlike superconductors, which face noise challenges as they grow, or ions, which struggle with scaling, neutral atoms seem to offer the best of both worlds. They don't just hint at the possibility of large-scale machines. They make the dream of a million-qubit quantum computer look more realistic than ever. And here's the kicker. 6,000 qubits isn't the finish line. It's a prototype, a preview of what could be built if this platform keeps advancing at the pace we've seen. For the first time, we're looking at a system that could not only rival, but potentially surpass every other architecture on the board. But as breathtaking as that sounds, the most shocking breakthrough of 2025 didn't come from superconductors or neutral atoms at all. It came from a chip built on something far stranger. A design rooted in exotic physics that many once thought was impossible. In February 2025, Microsoft unveiled something the quantum world had been waiting on for decades. The Majora 1 processor, the first chip built around topological qubits. Why is this such a big deal? Because topological qubits are different from anything else in the race. Instead of constantly fighting against noise and errors, they avoid them at the hardware level by design. They're naturally protected from many of the tiny fluctuations that wreak havoc in other systems. In theory, that means fewer errors, less overhead for correction, and a much smoother path to practical, large-scale quantum computing. Majora 1 doesn't yet run hundreds of qubits. In fact, it's still at the very early stage with just a handful. But the material breakthrough that powers it, combining indium arsenide with aluminum to host elusive Majorana 0 modes, could allow millions of qubits to be packed onto a single chip. That kind of density would dwarf everything we've seen so far, taking quantum from experimental machines locked in labs to processors that could rival, or even surpass, today's silicon chips in scale. Of course, there's still debate. Physicists are scrutinizing Microsoft's data, asking whether the company has truly demonstrated robust Majorana states, or if it's still an experimental glimpse. But if confirmed, Majora 1 represents far more than another incremental milestone. It's a turning point, a sign that quantum computing may be shifting from a patchwork of competing architectures to a new foundation that finally makes the dream of practical, fault-tolerant quantum machines achievable. From optimizing power grids and discovering new drugs, to simulating the universe and building machines that defy errors, 2025 wasn't just another year in science. It was a year when quantum computing turned from theory into reality. So here's the question. Which of these breakthroughs do you think will change the world first? The race is only heating up, and the answers might surprise us all. Drop your thoughts in the comments below, and make sure to check out the next video, where we'll explore how quantum computing could one day change your everyday life in ways you'd never expect.